Hello, this is Jude Socrates, and today's video is an introduction to subspaces, bases, and dimension. We have actually already seen 2.5 words in this title. We have seen the word basis when we talked about the standard basis set of vectors for Rn, and we see the word dimension where we say that Rn has dimension n. And of course, speaking of Rn, we called Rn Euclidean space. So we have seen the suffix space in the word subspace. So today we're going to learn what these concepts are really all about. So in this video, we will define the concept of a subspace W of Rn. We will define the concept of a basis for a subspace W. And we'll find out that the span of a set of vectors is actually one of the best examples for a subspace of Rn. We'll see more of that later. So we will see a version of the minimizing theorem which will allow us to find a basis for the span of a set of vectors as a subspace. And finally, we will define the concept of the dimension of a subspace of Rn, and we will learn why is Rn called n-dimensional Euclidean space. So here's our first definition. A subspace W of Rn is a non-empty subset of vectors of Rn such that if u and v are both from W and R is a scalar, then we also have that u plus v is also in W and R times v is also in W. We say that W is closed under vector addition and scalar multiplication. And we use this symbol, which looks like a stylized less than or equal to symbol, to say that W is a subspace of Rn. And when we write down this symbol, we call Rn the ambient space of W, which is another word for the surrounding space. Okay, so W is non-empty. It has at least one vector. So let's take any vector from W. And the definition says, if you multiply that vector by any scalar, that should still be in W. Well, the simplest scalar that we can think of is the number 0. And what happens when you multiply a vector by the number 0? You get the 0 vector. So the 0 vector is always a member of any subspace of Rn. So this makes sense. We've seen a couple of objects back in chapter 1. We saw lines that pass through the origin and planes that pass through the origin. Okay, so this definition tells us that if you have a subspace of Rn in general, it has to contain the 0 vector. Okay, there are two very easy examples of subspaces of any Rn. And because they're so easy, they're called the trivial subspaces. So the first trivial subspace is the subspace which contains only the 0 vector. So we just said that any subspace has to have the 0 vector. But what if that's the only vector in your subset? Well, it turns out that it's enough. If the subset contains only the 0 vector, it's already a subspace. At the exact opposite extreme, you have all of Rn itself, every vector in Rn. So why are both of these subspaces? Well, both of them are non-empty. They both contain the 0 vector. In fact, Rn contains all the vectors. What about closure? So let's talk about Rn first, because that's easier. We already know that if you have two vectors in Rn and you add them together, you get another vector in Rn. And if you multiply any vector in Rn by any scalar, you again get a vector from Rn. So Rn is obviously closed under addition and scalar multiplication. Now, what about the set containing only the 0 vector? So let's think about closure there. We need to get two vectors from this set. Well, there's only one vector, so we have to pick the 0 vector twice. Okay, well, what do we know? If you add the 0 vector to any other vector, including itself, you get the same vector. So yeah, the 0 vector plus the 0 vector is still the 0 vector, which is in that subspace. What about closure under scalar multiplication? You take the 0 vector and you multiply it by any scalar, you again get the 0 vector. So therefore, the set containing only the 0 vector is also closed under scalar multiplication. So obviously that's a very boring example. Here's something a lot more interesting. So it turns out that the span of any non-empty set of vectors is always a subspace. So we have seen examples of this that we have mentioned in the introduction. We said that a line passing through the origin, plane passing through the origin. It turns out that both of these are examples of subspaces because they're both spans of a non-empty set of vectors. A line is the span of one non-zero vector, and a plane is the span of two non-parallel vectors. So in general, if you have a non-empty set of vectors u1 through uk from Rn, then the span of S, which we can now call W, is a subspace of Rn. So let's talk about closure under vector addition. Take two vectors from the span of the set of vector. Let's call them V and W. So V is a linear combination C1U1 plus C2U2 up to CKUK. And similarly, W is a linear combination, but we need to use different coefficients because V and W don't have to be the same vector. So W is D1U1 plus D2U2 up to DKUK. So we now have these two vectors from the span. Let's add them together. What is V plus W? So you add those two linear combinations together, and then you use the commutative property. So let's bring C1U1 plus D1U1 together because they both contain U1. Let's put C2U2 next plus D2U2 and so on. Now from the distributive property, we have C1 plus D1 times U1 plus C2 plus D2 times U2 and so on as our linear combination for V plus W. So this says that V plus W is also part of the span of U1 through UK. Now we will leave it up to you to show that a scalar multiple of V is also a linear combination of U1 through UK. It's not very hard. So now let's talk about the concept of a basis. And again, as mentioned in the introduction, we saw the word basis when we constructed the standard basis vectors for Rn. So in general, a basis for a non-zero subspace W of Rn is a non-empty set of vectors B with the vectors W1 through Wk, which is a subset of W, which spans W and is also linearly independent. So when we first saw the concept of span, we said that the span of a set of vectors will always contain the individual vectors. So obviously, if W is the span of W1 through Wk, then all of these vectors should belong to W as well. So let's talk about the standard basis for Rn, which is the easiest example of a basis. So a reminder, E1 is the vector where you have 1 in the first component and 0 everywhere else. E2 is 0 in the first component, 1 in the second component, and 0 everywhere else, and so on. So when we first saw these vectors, I believe in section 1.1, we said that every vector x1 through xn from Rn can be written as a linear combination. So it's just x1e1 plus x2e2 and so on. So this tells us that the span of these vectors is all of Rn. You're not missing any vector at all from Rn. We talked about linear independence from our last video, and in fact, the standard basis vectors was our first example. So let's recap what we did in that section. First, you set up the test equation, the dependence test equation. You have x1e1 plus x2e2 through xn en has to add up to the 0 vector. But we just said that the left side is the vector x1 through xn. So we want to set x1 through xn equal to all zeros. Well, that means that all of the coefficients, x1, x2 through xn, they all have to be 0. And so our set is linearly independent, and therefore the standard basis set satisfies the two conditions required to be a basis for our entire vector space Rn. Okay, so we know that a plane is created with two non-parallel vectors from the plane. So let's consider the plane pi with Cartesian equation 5x minus 4y plus 7z is 0. Let's make a basis for this subspace, this plane. Okay, so B will be made of two vectors. Here's one vector. What will go in it? Well, we have to find x, y, and z that satisfy this equation, but it's 0 on the right side. So an easy way to do it is to make one of the variables 0 and then eyeball the values for the two other vectors. That will make it sum up to 0. So for example, if z is 0, so let's put a 0 over here, then what has to happen to x and y? Well, how about x is 4, because we have a coefficient of minus 4 here, so that will give us 20, and then to make 0, we have to make y 5. So x is 4, y is 5. Okay, so again, let's check. 5 times 4 is 20, minus 4 times 5 minus 20, plus 0, we get 0. We need a second vector which is not parallel to our first vector. So how about this time, let us make x 0. How about that? So if we make x 0, so this time, how do we make minus 4y plus 7z 0? Well, how about y is 7? So you get minus 28 because we see a 7 over here. And so z is positive 4. So y is 7, we get minus 28, plus z is 4, 7 times 4, we get plus 28, we get 0. So we have two vectors here, and they're obviously not parallel to each other, because if you multiply the first vector by any scalar, the last component is going to stay 0. And our last component here is 4, so there's no way you can get the second vector as a multiple of our first vector. So this forms a basis for our plane. We only need two vectors to create our plane. Okay, that just takes care of the spanning property though. And we said that we need two non-parallel vectors on pi to span the plane. And here we have two non-parallel vectors. What about linear independence? Well, if you read section 2.1, it was pointed out that if you have a set of two vectors, then those two vectors are linearly independent if and only if those two vectors are not parallel to each other. So the property of not being parallel actually helps out both for spanning and for linear independence. A set of two vectors is linearly independent if and only if they are not parallel to each other. All right, so that takes care of both spanning and linear independence, and therefore B is a basis for I. Okay, could we have made a different basis? Well, yes, of course. Okay, we just made it convenient. We said, Let's make z0, let's make x0, and let's make the rest of the vectors. Could we have made y0? Of course. Then x will have to be 7, because of that plus 7 here. So you'll get 35, so z has to be negative 5 to get 0. So you can make 7, 0, negative 5 as one of the vectors, and then you can pick another vector. So of course, this tells us that, wait a minute, we can choose one of an infinite number of vectors on this plane, and then make a second vector. As long as that second vector is not parallel to the first, then that also works. Okay? So a basis for a subspace is not unique. There are an infinite number of choices for a basis for a subspace. So what if our subspace is already the span of a set of vectors? We have a set of vectors w1 through wk, and then we create our subspace to be the span of that set of vectors. When is this set already a basis? Well, we already have half of the requirement, meaning you have to span your subspace. So we're only missing the second requirement, which is linear independence. So therefore, this set of vectors is a basis for the span of that set of vectors as a subspace, if and only if that set of vectors is linearly independent. Okay, great. But what if that set is dependent? So let's generalize the symbol, and let's use the symbol S instead of B. The trouble with using B is that it makes you think, oh, it's already a basis, B for basis, okay? So let's make it a little bit less judgmental, shall we use that word? So we have a set of vectors S, and we create the span of S as a subspace, W. And if S is dependent, well, we saw the minimizing theorem in section 2.1, okay? And we said, how did it work? You assemble your vectors into the columns of a matrix, you find the REF, and then you look for the leading variables, okay? So the columns corresponding to those leading ones form a linearly independent set of vectors, and they have the same span as the original set of vectors. And that's because the second half of the minimizing theorem says, if you are not included in this set, what we called S minus S prime, then you can be expressed as a linear combination of the vectors in S prime. So in other words, you are redundant. If you already have the vectors in S prime, you can create the other vectors which were not included in S prime. So we can adapt the minimizing theorem. We will call it a basis for a subspace version. Suppose you have a set of vectors w1 to wk from Rn, and W is their span. Create the matrix A. Again, we call that the matrix of S, made with the columns w1 through wk, and you get the REF R of A. Then the columns of A corresponding to the leading columns of R will form a basis for W. We have only one more concept left, so let's get that out of the way so that we can talk about applying the minimizing theorem, finding a basis for a subspace, and our last concept, the dimension of a subspace, all at the same time. So, what is the dimension of a subspace? Suppose that B and B prime are any two bases for the same non-zero subspace W of Rn. So we talked about a plane passing through the origin, our example, and we said, oh, this is not the only basis that we can make for the subspace. We can make y0, and then we can get a different vector, and then all you need now is a third vector, or I'm sorry, a second vector, which is not parallel to that vector, and these two vectors together will form a basis, another basis for that plane. But what is true for any two bases for the same subspace? They have to contain exactly the same number of vectors. So we need two vectors for the plane to create a basis for that plane. That number 2 is set in stone. You can't use only one vector to make your plane because that will just get you a line. If you have 3 linearly independent vectors though, it turns out that will get you all of R3. It's more than just the plane. In that case, you will get all of R3. So any two bases for the same subspace must contain exactly the same number of vectors. We call that number the dimension of W, and we write that the dimension of W is K, and K has to be at most N. K cannot be bigger than N. We also say that W is K-dimensional. Now, the zero subspace does not have a basis because, well, the only candidate is the zero vector, and we saw in section 2.1 that any set containing the zero vector is automatically dependent. A basis has to be independent. So therefore, the trivial subspace made only of the zero vector does not have a basis. So we will say that the dimension of that trivial subspace is 0. On the other hand, the dimension of W is a positive integer for a non-zero subspace W. So let's apply this to the two examples that we already saw. We said that the standard basis consisting of E1 through En is the basis for Rn. So what is the dimension of Rn? Well, how many vectors are found in this basis? We have n vectors, so the dimension of Rn is n. Of course, we already knew that from section 1.1. So since there are n vectors in S. What about our second example? We made a basis for pi and it had 2 vectors. So the dimension of pi is equal to 2. That makes sense, okay? Any flat surface, we call it a 2-dimensional surface. So a plane is a 2-dimensional subspace of R3. All right, so now let's apply the minimizing theorem. Suppose you have W is a subspace of R5, and it's given as the span of a set of vectors S, where S has 6 vectors. Ooh, that's a lot of vectors. So here are the 6 vectors making up S, and if those vectors look familiar, we use this example in section 2.1. So let's find a basis for W. We have 6 vectors for R5, and we also saw in section 2.1 that as soon as you have more than 5 vectors from R5, then that set is definitely linear independence. Why? We can see it from applying the minimizing theorem. Put the 6 vectors as the columns of the matrix. So we get a 5 by 6 matrix. That is an underdetermined system. In this case, it's a homogeneous system because we're testing for linear independence. And so we will get at least, and therefore our set is linearly independent. So, are linearly dependent. So let's look for the RREF, compute matrices RREF. And yep, we get 1, 2, 3 free variables and 3 leading variables. So therefore, our basis for for W is made of column 1, column 2, column 4, which are V1, V2, and V4. So we have V1 and V2, and we have V4. So these three vectors make up our basis for W. And what is the dimension? We have three vectors, so the dimension of W is B. Is 3, I should say. Okay, so even though we started out with 6 vectors in our spanning set, they're far from independent. Okay, you have 3 redundant vectors, and the minimizing theorem says you only need V1, V2, and V4. Now, before we move on to our final example, let me just mention this theorem that tells us that every subspace of Rn does in fact have a basis. So we saw this demonstrated for our plane. We started with one non-zero vector from our plane. Is that enough? No, you need 2 vectors. So we pick a second vector on the plane, which is not parallel to the first. And then we ask, is that enough? Yes, for a plane, we know that that's enough. So in general, as you will see in the proof of this theorem, you might have to keep going. So if you're in R7, for example, maybe you need 5 vectors to make a basis for your subspace. But you need what's called the extension theorem to keep adding vectors to your basis. So you start out with 1 vector. Is that enough? Maybe, maybe not. You need to add a second vector, which is not parallel to the first. That means you get a vector which is not in the span of the first vector, but still inside W. So now you have 2 vectors. They're still linearly independent according to the extension theorem. Do you need a third vector? Maybe. So if you do, you pick a third vector from W, which is not in the span of the first 2 vectors. And according to the extension theorem, those 3 vectors are still linearly independent. So now that you have 3 vectors, is that enough? You keep going. Maybe it is, you can stop. Maybe it's not. You need a 4th vector. Pick a 4th vector not in the span of the first 3. By the extension theorem, the set of 4 vectors is still linearly independent. So you keep going, and we know that this has to stop because as soon as you have 8 vectors from R7, that's a linearly dependent set. So you had to stop somewhere before that step. So that tells us that no matter which subspace you pick of Rn, you can always find a basis for that subspace, and the number of vectors in that basis is at most n, the dimension of your ambient space. Now, it's a little bit harder to show that any 2 bases, which is the plural of bases, for the same subspace has exactly the same number of vectors. So to do that, you need what is called the independent sets from spanning sets theorem, and that is proven at the end of that section. So be sure you read that, and that will complete the proof that any 2 bases for a subspace must have exactly the same number of vectors. Okay, so as our final example, we have another subspace made as the span of a set of vectors, this time from R6, and we have only 4 vectors. So in our last example, we had 6 vectors from R5. Now we have 4 vectors from R6. It's no longer an underdetermined system. In fact, it's now overdetermined. There are more rows. There are 6 rows and only 4 columns. So we are not guaranteed a free variable. Maybe we will get all leading variables. Maybe we will still get a free variable. So we won't know until we click compute matrices REF. Okay. So we get 3 leading variables and we still have a free variable. So therefore, this set is dependent, but the vectors corresponding to the first 3 columns, which means the first 3 vectors in our set, gives us a basis for our subspace. Since we have 3 leading ones, we also have a 3-dimensional subspace. Okay, so let's write down our answer over here. We said we need the first 3 vectors. So we have 1, 2, and 3. So that is our basis for W. And since we have 3 vectors, the dimension of W has to be 3. My bad, I lied to you. I actually have one more example for you. Let's change S just a little bit. So we're going to call it S2, and W prime is the span of this slightly different set, S2. We are just going to change -7 ever so slightly to -6. So how is that going to change the REF? Compute matrices REF. And we get, so now this time we have 4 leading variables and no free variables. Okay, so what does that mean? S2 is now linearly independent. It is no longer a dependent set. So S2 is already a basis for W prime, and so the dimension of W prime, let's change that over here, must now be 4 instead of 3. Okay, so let's write down our conclusion over here. So we said that S2 is now linearly independent, and so S2 is the basis for W prime, which again is the span of S2. And we also can say that the dimension of W prime is now 4 instead of 3. All right, we have reached the end of our video. Thank you so much for watching. I hope that you understood the concept of a subspace, basis, and dimension a little bit better after watching this video. So until the next time, enjoy the rest of your day.